A geometric sequence is a sequence where each new term is found by multiplying the previous term by the same number. That number that we're multiplying by is referred to as a common ratio, and we can find that common ratio by taking a term, dividing the term right before it, and that will tell us what we multiplied by. So for example, -8 divided by 4 is +2. -4 times 2 is -8, times 2 is -16, times 2 is -32. So the common ratio in that first sequence is 2. Again, what are we multiplying this by to get to this number? If you're not sure, take this number, divide by the one right before it. So -5 divided by 10, -5/10 will reduce to -1/2. And you'll notice on this one, we have a positive term, a negative term, a positive term, a negative term. If the common ratio is negative, when we multiply positive times a negative, we get a negative. Negative times a negative, we get a positive. So those signs are going to alternate as we move along the sequence. This particular one, if we take 1/3 and divide by 1/9, now remember when we're dividing fractions, we end up multiplying by the reciprocal. So we're going to flip that 1/9 over, and then 9 divided by 3 is 3, so that will give us the common ratio in that last sequence. So if we have a general geometric sequence, we start with term 1, term 2, term 3, and we continue on until we get to this is our last term or general term. Let's look at how we can calculate the value of what that term would be. Okay, so term 1 we know is just term 1. We know that we're multiplying by a common ratio to get to term 2. So term 1 times 1 common ratio gives us the value of term 2. Then from term 1, you can see we're multiplying by 1, 2 common ratios to get to term 3. Now be careful here. A ratio times a ratio, remember when you multiply powers with the same base, you're adding the exponents. So this becomes r squared, it's not 2r. So remember you're multiplying r times r, add those exponents, we get r squared. We're going to multiply by another common ratio to get to term 4. So r squared times another r, add those exponents, and we have term 1 times 3 common ratios. So that process is going to continue until we get to this term. So if I tell you we have term 1 times 9 common ratios, what term would we be on? And hopefully, looking at the pattern here, you can see that we would be on term 10. And then we can continue that process until we eventually get to that last term in our sequence. So in order to calculate that last term, if you take a look at the pattern here, you'll notice that we have term 1 in each of these. And then from term 1, we are multiplying by one less common ratio than that term number. So we multiply by 2 common ratios to get to term 3. We multiply by 3 common ratios to get to term 4. We multiply by 9 common ratios to get to term 10. So we're always multiplying by one less common ratio than the term number that we happen to be on. So we're able to calculate the value of any term by taking term 1 and then multiplying by one less common ratio than we happen to be on. The first thing we want to do with a sequence is determine, is it actually geometric? It could be arithmetic or it could be neither. So if we take a look here, I can see that 2 times 8 will give me 16, and then you need to check every term. 16 times 8, will that give you the next term? If it does, we know our common ratio. So our common ratio in this case is going to be 8. We need to find term 7 as well as the general term for this particular sequence. So we could just multiply by 8 all the way along here. It is a little time consuming, but we can get the value of that 7th term. Or we can use this formula and say, okay, term 1 we know is 2. If we're getting to the 7th term, we're multiplying by 1, 2, 3, 4, 5, 6 common ratios. So we can substitute that into the formula. Remember, you need to do exponents before multiplication, and we can get the value of term 7. So you can see we get the same value either way. Or we could also say the last term that was given to us was term 3. From term 3, we're multiplying by 1, 2, 3, 4 common ratios. So we can manipulate that formula and say term 3 times 4 common ratios, substitute in the value of term 3. We know the common ratio is 8, and again, we will get the same value for term 7. So there's different ways you can go about this once you understand how a geometric sequence works. Now, in terms of getting the general term, we are looking for a formula that no matter what we substitute in here for n, we're going to be able to get the value of that term. term. So let's begin with that general formula, and we can substitute in what we know. So we know term 1 is 2, we know our common ratio is 8, and we want to keep n in that formula so we can substitute anything in and find the value of that. Now this is simplified. The exponent on this 2 is 1. We cannot combine those together. They are not powers with the same base. So do not multiply those together. This is the simplified form, and then you can test this. So let's maybe try the second term because that was given to us. If we go 2 times 8, will that give us 16? If we put the third term in, so we know n is 3, 3 minus 1 is 2, 8 to the power of 2 is 64, 64 times 2, does it give us that value? So test your general formula, make sure that it works for the terms that you are given, and then you can apply it to any term that you need to find. In our next question, we're given a sequence and asked to determine how many terms are in that sequence. So we're looking for the value of n. The first thing we need to do is check what kind of a sequence is it. So we can see in this case we are multiplying by 3 each time. That makes it a geometric sequence. And so we can take our formula. The last term in our sequence is that 135. The first term in our sequence is 5, and our common ratio is 3. We're looking for the value of n. Now remember, we cannot multiply those together. This is an exponent of 1, this is an exponent of that. These are not the same base. We cannot multiply powers together if they have different bases. So what we're going to do instead is we're going to divide out that 5. So 5 divided by 5 is 1, so that's gone. 135 divided by 5 will give us 27, and then we're still left with that power. And at this point, we have an exponential equation because we have an exponent that's a variable, but we don't actually learn how to solve exponential equations until we get to the next course. So we're going to get kind of a preview here. Let's say that I told you we had 2 powers with the same base and they were equal to one another. So if the exponent on my first power is 3, what would the exponent on this power have to be? And hopefully you can see it would be 3. If I give you 3 to the power of 8 and I tell you it's equal to 3 to the power of something, what would that exponent have to be? Well, it would also be 8. If I give you negative 5 in brackets to the power of 3 halves and I tell you it's equal to something with the same base, we know that that exponent has to be the same. So if we have 2 powers that are equal with the same base, therefore their exponents also have to be equal. So if we take a look at this, we can see we have 1 power here on the right. Is it possible to write this left-hand side as a power with the same base? So 3 to the power of something, will that give us a value of 27? And we can see that 3 cubed is 27. So now once we have 2 powers that are equal to one another, if the base is the same, therefore we know the exponent must also be the same. So now we can algebraically solve for n, add 1 to each side, and when we do that, we get an n value of 4. And then you can always check this. So substitute it back in. We have 5 as term 1. 3 is our common ratio, and we have 4 minus 1 is 3. Does that give us a value of 135, which is the last term in this sequence? And it does. So in this case, we don't actually need those ellipses. There are 4 terms in that sequence. In this next one, we're also looking for n, the number of terms, but we're now going to throw some variables in here. So the last term we're given is this x to the power of 21 over 27. The first term is that 243 times x to the power of 5. We have our common ratio, and we're looking for n. So again, when we see something like this, the first thing you want to do is divide out that first term. When we divide fractions, remember we're multiplying by the reciprocal. So I'm going to flip this upside down. The denominator is currently 1. That goes on top, and then we still have the right-hand side as is. So now when I go to multiply fractions, we're multiplying the numerators and we're multiplying the denominators, but I can see that we're going to be dividing 2 powers with the same base. When we divide 2 powers with the same base, we're going to subtract those exponents. So 21 minus 5 is going to give us 16, and then we can multiply those numbers on the denominator. And then at this point, remember, we're looking for that common base. So is there a way that we can get this as x squared divided by 3? And I'll give you a hint. Let's start by checking. In order to get x squared on top, I would have to put an 8 on the outside of the bracket. So then we can check, would 3 to the power of 8 give us that value? And if so, we've now got our 2 powers with the same base. If the bases are equal, therefore the exponents must also be equal. So now we've got a linear equation. We can add 1 to each side in order to solve for n. And now we can check it. So we think there are 9 terms in this sequence. So we're looking for term 9 should be that last term that we're given here. So substitute in the first term and our common ratio, and then 9 minus 1 will give us 8. And then if we have a power raised to a power, remember we're multiplying those exponents. So we're going to get x to the power of 16, and then 3 to the power of 8 is 6,561. And then I'm going to multiply powers with the same base. We're going to add those exponents together. This is a denominator of 1. 1 times 6,561 is still 6,561. And then these both divide evenly by 243. So we can divide those to reduce the fraction. And in the end, we get the 9th term, which is the last term in this particular sequence, is x to the power of 21 divided by 27, which is what we were given. So we know we got the correct number of terms. In our next example here, we're told that we have a geometric sequence. We're given the value of the second term, and we're given the value of the 5th term. We're asked to determine the first term and the common ratio, as well as to list the first 3 terms of the sequence. So we can begin similar to how we did with arithmetic sequences, where we can pull kind of a mini sequence out of here and say if this is the first term, we're multiplying by 1, 2, 3 common ratios in order to get that term. So we can set those values into our formula here. So the last term in our mini sequence is that 1792. We have the first term as 28, and we're looking for the value of that common ratio, knowing that we have 3 of them to get from here to here. All right, so the first thing we're going to do is divide out that 28. We're trying to isolate r, and when we divide out 28, we get r cubed isolated. In order to get rid of a cubed, I'm going to cube root, and when we do that, we get the common ratio of 4. So in order to find term 1, I'm now going to divide by 4, and so when we do that, we're going to get 7, and then when I'm going this way, I'm going to multiply by 4, and we can fill in the other terms within this sequence here. We're only asked for the first 3, but we can fill in all of them just to check, are we multiplying by 4 all the way along? We encountered a similar question like this when dealing with arithmetic sequences, and the other way we can solve an arithmetic sequence was with a system. If we're dealing with geometric sequences, I'll just show you what happens here. So we know that the 5th term is 1792, so I can put in 1792, and I get to that by taking the first term and multiplying by 4 common ratios. I know that my second term is going to be term 1 times 1 common ratio, and when I substitute in the value of that second term, we end up with 28. I cannot subtract these because this is now 1 term and 1 term, and these are not like terms, so we can't subtract. So what you have to do with geometric is we end up actually dividing those two systems. So we're going to go 1,792, we're going to divide by 28, and that will give us 64, and then term 1 divided by term 1 is just 1. R to the power of 4 divided by r. Remember, when you're dividing powers with the same base, we're going to subtract exponents. So we get r cubed, and again, when you cube root each side, we end up with the common ratio of 4. So you can see that we get the same value. With geometric, however, you're dividing the systems instead of subtracting. Now I want you to notice what happens with this next example. So we're given term 4 and we're given term 6. We have to find the first term and we also have to find the general term. We're told it's a geometric sequence. So we can begin the same way. So from here to here, I'm multiplying by 2 common ratios. So we can go ahead and set that up. I'm going to divide out that negative 375, leaving me just with that r squared. And then in order to get rid of the squared, we're going to square root. And then remember, when we square root, because this is a variable, we're going to end up with a positive and a negative root. So we're going to get positive 5 as well as negative 5 for r. There's 2 potential common ratios, and that occurs if the exponent on r is an even number. In the previous example, that exponent was an odd number, in which case we're not going to end up with the 2 cases. Let's say that r is positive 5. If r is positive 5, then again, we can say, okay, if this is the last term in our mini sequence, if we're now going to pull from here to here in order to solve for term 1, we're looking for term 1, we're multiplying by 1, 2, 3 common ratios to get there. So 5 cubed is 125, divide that out, and term 1 would be negative 3. And you can check this, negative 3 times positive 5 times positive 5 times positive 5 will you get here. And then in terms of our general sequence, we're going to have term 1 times our common ratio of 5, and then n minus 1 as the exponent. When this occurs, every term will be negative in this sequence. We're beginning with a negative term and we're multiplying by a positive ratio. So negative times a positive is negative, times a positive is negative, and so on. If r happens to be -5, so we can substitute that in, again, pull a mini sequence here. So we're looking for term 1. We know that we have term 4 is -375. We're multiplying by 3 common ratios to get there. -5 cubed is now -125. Negative divided by a negative is a positive. So now we have a positive term 1 given that negative ratio. And now if this is positive and we multiply by a negative, we're going to get a negative. A negative times a negative is a positive. A positive times a negative is a negative. Now your terms are going to alternate, positive, negative, etc. So you need to be careful in geometric sequences. If at any point you're trying to solve for the common ratio and you have an even exponent, you're going to get both a positive and a negative ratio. One thing I just want to remind you of also that you need to be careful of is, depending on the problem that you're given, make sure that you count the number of terms correctly. So I'm going to just take a look at one of the questions from your textbook. So we have jeans, and every time we wash those jeans, we're losing some of the color. So if the jeans fade by 5% with each washing, that means 95% of the color will remain. So that is our common ratio. If we start with 100% of the color, multiply, we're taking 95% of 100, so change your percent to a decimal and multiply, and then 95% of 95, 95% of that value, and so on. So that common ratio is 95%, which as a fraction is just 19/20ths. We're asked to determine the percent of the color remaining after 10 washes. So if you think about your question, this is the starting color. After 1 wash, we're on term 2. After 2 washes, we're on term 3. So after 10 washes, we're actually going to be on term 11. So 11 minus 1, when we put it into the formula, gives us that exponent of 10. So we're going to have about 59.87% of the color left. How many washes would it take so that only 25% of the original color remains? So this is what we want left at the end. So that is going to go in for T sub n. We started with 100%. So 25%, 100%. Now at this point, again, we're going to divide out that 100. 25 divided by 100 is going to give us a quarter. Is there a way that we can get the same base? And you're going to see in this case we can't. So in the next course you take, you're actually going to use logarithms to solve this. But at this point in time, you kind of have to guess and check. So you're going to grab your calculator and you're going to say, okay, 0.95 to the power of what is going to give me a value close to that 0.25. So try maybe 26, and you're going to see you're a little too high. Try 27, that's pretty close. It's not exact, but it's close. Try 28, see if you can get closer, and no, you're further away. So when you get to this point here, if you cannot get the same base, you have to guess and check. So we're going to see 27 is the closest value, and that's assuming that your jeans will fade at the same rate.